we have Vilasini coming to speak to us today about composable security and relativistic cryptography. So thank you very much.
Great. Thanks very much. First of all, thanks a lot, Max, for organizing this visit, and Marcus as well for inviting me. This is actually, I'm really excited to be here and talking in person after so long. It's really the first in-person research trip in more than a year and a half, so I'm very glad to see all of you here in person. And one thing I should clarify, because it's always the first question I get after every talk, Vilasini is my first name. We just write it that way because usually where I come from, the south of India, the last name is usually the first name of our fathers. So I prefer to be addressed as Vilasini, so Vilasini. But anyway, that's my first name in case you want to address me. Right, so today I'll be talking about this work on composable security and relativistic cryptography. And this is joint work with Christopher Portman and Lydia Del Rio, who are both at ETH Zurich. And paper is already 2 years old. You can find it here. So here it's in the New Journal of Physics. Okay, so let's get started. So let me first unpack the title, tell you what this talk is about, and I'll take that opportunity also to give you an overview of what you can expect in this talk. So if you find it too boring, you also have the chance to, that's your moment to leave. I'm kidding. So this gives you what's on the menu for today. All right, so the first thing that's on the title is composable security. And the motivation for this is that ideally when you build or when you talk about a cryptographic resource, the idea is to then use it as subroutine in other tasks to build other cryptographic resources. And you want a notion of security that's stable under such compositions. So if you prove that a certain resource, some cryptographic protocol is secure, it should remain secure when it's used as a subroutine in any arbitrarily other protocol. And this is what the idea of composable security is at an abstract level. Right, and the second thing is that at the physical level, you want to instantiate these protocols in some physical settings. And what we want to consider here is a general class of scenarios where, of course, you want agents to exchange quantum systems. And more generally, you can consider agents who are measuring post-quantum systems as well. And we also want to consider the relativistic aspect, which is we really take into account the space-time locations of these agents. And then both agents and adversaries in the protocol would be limited by relativistic causality, which is at least at a minimal level that they can't signal superluminally. And finally, there was, prior to this work, no sort of framework where you could talk about composable security of very general class of relativistic and quantum, post-quantum protocols. So we proposed such a framework here. And then we use this to prove some new possibility and impossibility results in the field of relativistic cryptography. So this is more fundamental limits on what can or cannot be done, like what kind of tasks can be achieved in a composable manner. So I will first give a bit more motivation for composable cryptography by giving you some examples to see why this is important, why we should care about this. And then I will tell you about the framework of how you can actually talk about composable security of the general class of protocols, and then I will get to the results of what are possible and not possible, and so on. All right. Okay, so let's start with a very simple protocol, which is coin flipping. And the idea of a coin flipping resource is that it's a resource shared by Alice and Bob. And what it does is simply outputs a uniformly random bit, C, to both Alice and Bob. So the important assumption we need here, or the important condition that this resource should satisfy, is that C is independent and also uniform. So it's not correlated with anything else, right? Okay. So of course, now this is the definition of the resource I want. One can ask what would be a protocol that would construct this resource in a secure way. And we are assuming that Alice and Bob are mutually distrusting parties. So in the rest of the talk, we will look at two-party protocols where the adversary is not external, but the parties don't trust each other. So for Bob, Alice is the adversary, and for Alice, Bob is the adversary. So in this case, of course, the obvious thing that either Alice or Bob flips the coin and tells the other will not work because they don't trust each other. And the first guess, for example, would be that let's imagine that Alice and Bob each consist of two trusted agents. So there's Alice 1 and Alice 2, who trust each other, Bob 1 and Bob 2, who trust each other. And then you could say that, okay, let's pick two spatial locations, x1 and x2, and there's one representative of each agent at each of these locations. So yes, and then you want to ensure that everything takes place within a time interval that ensures that there's not enough time for light to go between these two space-time locations. And then what Alice does is that she picks a random bit A and gives it, so Alice 1 picks a random bit A and gives it to Bob 1 at some time t1. And Bob picks a random bit B and gives this to Alice at some time t2. And if you can ensure that these two are space-like separated points, then you could maybe convince yourself that, okay, they could not cheat. And in the end, they output a C, which is just the XOR of A and B. So on the face of it, it seems like this should work, at least if you ensure this space-like separation. So I'll now tell you why this protocol, this simple protocol, would not be composably secure. So in particular, if you try to do two instances of this protocol in parallel, then the agents can coordinate, and basically the protocol is not secure anymore. Yes?
Question. I didn't quite understand what's the goal of the two is so they'll perform the XOR of their bits, and then you'll get another bit, and if it's 1, say, then Alice wins, and if it's 0, then Bob wins, is that? Or?
No, sorry. So basically what they want to construct is a resource that does this, that basically, in the end, they have to end up with the same random bit, Alice and Bob, but they trust that this bit is independent and uniformly distributed. So this resource is useful because, for example, if the two of us have a dispute and we want to settle it, we want to flip a fair coin that gives the same outcome. But of course, if you flip the coin, I won't trust you, and if I flip the coin, you won't trust me. And this is one potential protocol by which the parties could be convinced that that in the end, because Alice picks one part of it and Bob picks one part of it to get the final coin flip, on the face of it, it seems like this, the parties could be convinced that this is a fair way to settle their dispute. Does that answer your question? Yeah, cool. Okay, so let's look at what composability issues arise here. So let's say we have two instances of this protocol, one between Anushka and Bob, the other between Charlie and David. And so they're basically just implementing the protocol that I showed you before. But now imagine that if Anushka and Charlie could coordinate amongst themselves and talk to each other, then they can arrange it so that in the end, the outcomes of both the coin flips are perfectly correlated. And the reason this is not secure is because this doesn't construct the ideal functionality we talked about before, where you want, for each coin flip, the outcome to be independent and uniformly distributed. So this means that pairs of parties cannot settle disputes independently with such a resource. And in fact, a lot of cryptographic constructions based on coin flipping, for example, you can do things like multi-party computation and more complicated but still more useful tasks if you're given a secure coin flipping resource. All this cannot be done if this resource does not output independent and uniform bits. Right, and what has been shown is that, of course, the protocol I showed you before, Alice and Bob did not start off with any shared resource, like a secure channel or some other resource. We didn't make any assumptions on what they start off with. But it has been shown that such an attack can be avoided if we assume that each pair of parties who are implementing such a protocol share a resource known as bit commitment, or secure bit commitment resource. So then let's look at what bit commitment is, because then it would allow you to do coin flipping in a secure way, and then coin flipping can allow you to do other things in a secure way. Right. So bit commitment itself is quite a simple resource. So okay, maybe I make a comment. So when I talk about resources in this manner, this is we're describing some abstract and ideal functionality that we would want to get out through some physical protocols, right? So this is what we want, and then we will try to come up with protocols that will construct this, and then we want to show that these protocols actually securely construct this. So this was also the case with the coin flipping example. What I had first was a description of the resource. Then we saw that the protocol I proposed does not really construct that resource because you have this man or woman in the middle attack. Right. So with bit commitment, we have two parties again, Alice and Bob. And Alice we will call the committer, and Bob is the receiver. And as the name suggests, what Alice has to do is she picks a random bit A, just a classical bit, and she has to commit to it. So she does so by inputting it to this resource. And once she does that, Bob gets a message saying that, hey, Alice has committed to a bit. This message doesn't reveal the value of the bit, but it lets Bob know that Alice has now committed to a bit. Then at some later time, Alice can decide, okay, now I'm ready to reveal my commitment to Bob. And she can input to the resource saying, okay, open my commitment. And then Bob receives the value of Alice's bit. And broadly speaking, there are two security requirements for this. So the first thing we need is that the protocol is, or the resource is hiding, which means that Bob should not know the value of A before it's actually opened and before he actually gets this outcome. So between this sort of commit phase and open phase, Bob has no information about what Alice committed to. And the second, it needs to be binding, which is that once Alice has committed to this A, she cannot change the value of A. So these are the two, broadly speaking, these are the two requirements that are needed of bit commitment. So you can maybe think of it as I have a key to something, or I have some message that's a secret. I put it in a box, I lock it, and I give someone the key, right? I give Bob the key. Then Bob has the key, and he knows that if the key is my only way to open this box and change the message, then he can be quite certain that I probably can't tamper with it until I hand the box over to him myself. So that's the sort of idea. So the security window is really between these commit and open phase, where neither of the parties can really go and change what's in the resource. Right, and bit commitment is an important cryptographic primitive. You can do all these other things, so this is known in the literature. You can do very cool things like multi-party computation. You can do zero-knowledge proofs. So for example, if Alice wants to prove to Bob that she knows the proof of Riemann's hypothesis, she can actually do so without actually telling him the proof. So she can convince him that she knows the proof, that it's a valid proof without actually revealing the proof to him, which is quite interesting. Right, so let's see what's known so far about bit commitment, right? So one thing to consider is, okay, now if I have no assumptions, no prior resources shared between Alice and Bob, is there a protocol that can securely construct a bit commitment resource of the kind we described before? So I will call this bit commitment solely through the exchange of messages. So they can communicate with each other, but there's no assumption that the channel is secure or something like this. Yes, so let's see what is known. So for example, in the non-relativistic case, it has been shown, so if you only focus on standalone security, which means that I'm not looking at composable security, I'm just looking at whether a single instance of this protocol between an Alice and Bob is this secure. Then it has been shown that this is already not possible in the quantum case, because there is a quantum attack against such protocol, and it's actually quite a nice argument. It's based on Ullmann's theorem. So maybe I can just sketch the argument briefly. So imagine that now Anushka and Bob are trying to run a bit commitment protocol, where Anushka wants to commit to a bit, small a, and Bob is the receiver, right? And let's say that there is some joint state, psi, superscript a, which is basically describes the joint state that Alice and Bob have in possession after they exchange all these messages, in the case where Alice commits to some bit a. Right, so now, if you recall, we had one property, one of the security conditions that we needed was that the protocol has to be hiding, which means that at this point, so if this is the state right after Alice commits to a bit but has not opened to the bit, at this point, the state should not give Bob any information about what the bit was. So you want this reduced state for either value of a to be the same on Bob's side. But on the other hand, we know that these two states are really purifications of the same row, right? Two different purifications. And we know that that means that there is a local unitary on Alice's side which can flip between these two purifications. So which means that it's not binding on Alice. This means once she has committed to a bit, without Bob ever realizing it, she can apply a local unitary to flip her commitment. So this could never be secure. Right. And on the other hand, so this was standalone security, But for composable security, there's already like a classical attack, which is precisely this sort of man or woman in the middle kind of attack where parties can collaborate with each other and make two instances of the protocol insecure. And this is already shown impossible for classical case. And again, I can maybe give you some more intuition for this. The reason this would be a problem is that imagine that Bob and Charlie want to implement some bit commitment scheme. But there could be other parties, say Anushka and David, who insert themselves in the middle of this protocol without the knowledge of Bob and Charlie. And then what they could achieve is a situation like this, where Bob and Charlie cannot distinguish whether they're running a bit commitment protocol between themselves or whether they're actually indirectly committing something to David and then Anushka is committing something to Bob. And this can be a problem. So like an intuitive example is imagine a chess game. Let's say that I'm a malicious party who is playing two chess games. In one game, I'm playing black, and the other, I'm playing white. So I wait for the person playing white to make a move, and then I just mirror that move on the other board that I'm playing against the black person. I just kind of do the same, and every time someone in the other game moves, I do the same. And so basically, I'm not making any of my moves. I'm just kind of pitting those two players against each other who have no idea that they're actually playing against each other. But now the way that the ELO system works, okay, let's say that obviously I will lose one game and I will win one game, most likely at the end. And most likely it will be the person who is a better player who will win the game. And the way that the ELO rating works is that if you lose against a good player, and you win against someone who doesn't have a very high rating, you have a net gain in the end. So someone doing this attack could, in the end, increase their ELO ratings in principle without actually being a very good player at all. Right? So that kind of roughly illustrates what the problem would be. Right, and so because of all these composability issues, I mean, not just composability issues, but also this quantum attack I mentioned, relativistic protocols have been proposed. And one of them is Adrian Kent's protocol in 2012, which actually showed that you can have standalone secure bit commitment if you allow for this set of parties who are space-like separated and so on. And the idea there is really that Alice now has to split into these two space-like separated agents. And then both of these agents of Alice have to actually, in the opening phase, reveal the correct bit. And then Bob can check this later and make sure that both of them actually did the right thing. And the reason that this avoids this, this quantum attack that I showed you before with this local unitary is because in order for Alice to change her commitment by doing this local unitary, this unitary would have to act jointly on both these Alices. But since they're space-like separated, this can't really be done. And so this is secure against this quantum attack that I mentioned before. Right. And then the natural question is, are such protocols composably secure? Can they be composed together in arbitrary manner and still remain secure? And there are some arguments in the literature which hint that, okay, this should not be possible, at least for this particular protocol. But there are many other bit commitment protocols that have been proposed in the relativistic setting. So in order to see if these are composably secure, you really need a rigorous framework to talk about it and model security there. So that would sort of be the goal of our work here to answer this question. So yeah, that's a summary of what I told you so far. Right, and maybe one more thing to mention is also like these bit commitment protocols, like the one by Kent, they typically allow for timed commitments, right? Like in the resource that I described before, there was no time constraint on how long Alice can wait before she opens the commitment to Bob. But in these relativistic protocols, this is basically limited by how long it takes for light to travel between these parties. So it acts more like a channel with delay. So we also would like to kind of formally define what this channel with delay does. Okay, so that's sort of what we do here. Give the framework, define this channel, and then look at some new possibility and impossibility results. And spoiler alert, it does turn out to be impossible to do bit commitment in a composably secure way through any of these class of protocols, at least if you don't assume anything. So if you don't assume any secure channel and other resources shared between the parties. Right, okay, so now for the framework. So the framework is basically consists of two parts. One is sort of the composable security definitions, and how do you model security, and this comes from this is inspired by the Abstract Cryptography framework, which was developed by Uli Maurer and Renato Renner. But this is, as the name suggests, quite an abstract framework, and we have to instantiate it with some physical systems, and for this we'll use the Causal Boxes framework, and I will tell you briefly about both of them. Right, so in the Abstract Cryptography framework, a resource is basically a system with some interfaces. So we've seen some examples before. In this case, we're only considering two parties. So Alice has an interface, Bob has an interface, which means that they can input some messages and receive some messages at their own interface. Right. And we also, we are going to model each resource as a tuple of 3 elements, basically. And this is going to tell us how the resource behaves. For example, this R will tell us how this resource R behaves when both Alice and Bob are acting in an honest manner, in the ideal manner that you would want them to act. But given that these parties don't trust each other, either one of them could be dishonest. So for example, now this RA would be the resource in the case where Alice is dishonest, and RB would be how the resource behaves when Bob is dishonest. This is because if one party is dishonest, they could, in principle, try to gain access to more controls on the resource. But we'll see particular examples of this. So again, as we saw, this was the coin flipping example we saw before. And when we say that the coin flipping is unbiased, in this case, irrespective of whether Alice and Bob are dishonest or honest, the resource behaves in the same way. Alice and Bob have no inputs to the resource. They only ever receive this outcome of the coin flip. But on the other hand, you can also consider a biased coin flipping resource. And here what happens is that, say, Bob is being dishonest. Then Bob can choose to receive the outcome of his coin flip, C, and then based on this, input a bit B into the resource, such that depending on B, Alice's output here, C subscript O, will be biased towards what Bob sent in, so in a probabilistic manner. So Alice's output will, with probability P, be equal to Bob's input, B, and with probability 1 minus P, it'll just be what the coin flip would have sent out anyway, which was the bit C. Okay? And similarly, if Alice is dishonest, she can do the same and input some input bit and try to bias Bob's outcome towards that. Right. So now another thing we need in order to model security of such protocols is a metric or a notion of distance between various resources. So we want to, we have these sort of ideal constructions which we want to achieve, and then we have real-world protocols that we would try to use to construct them, and then we want to say that in some sense this construction is epsilon close to the ideal thing. And we need some notion of distance between resources. And so this is basically done using this construct of a distinguisher. And what a distinguisher models is essentially the environment of a resource or a protocol. So you can think of, for example, the distinguisher is given a black box, which could either be this ideal functionality that I've described, or it could be the real protocol that's used to construct this ideal functionality. And the distinguisher can interact with this black box in any way it likes. And then in the end, it has to output a 0 or 1 to guess whether it's the real system or the ideal system that it was interacting with. And really the notion of composable security comes from the distinguisher, because this really models various information processing steps that can happen in between the protocol, after it, and so on. So in fact, the distinguisher can internally run a copy of the protocol in parallel and things like this, and it can try to ensure that it can't really distinguish between the real and ideal. So for example, in this, when you have this man-in-the-middle attack, a distinguisher running these things in parallel can see that the ideal system would never correlate these two, but the real protocol that I had before would actually have correlations, and then this can be used to gain a distinguishing advantage between these two. Right. Okay. So this is basically what I said, and the distinguishing advantage is basically defined as this maximum probability with which the distinguisher can distinguish between the real and the ideal system. Yes. And it's typically done with respect to a certain class of distinguishers. So for example, you could say I have computationally bounded distinguishers, or I have distinguishers that can be quantum, and so on. And then your notion of security, how strong your security is, will also depend on which class of distinguishers you've allowed. So is it, so that's a nice way to sort of see how strong your notion of security is. Right. So now more explicitly, I can actually tell you about the security conditions. So of course, the first one is what I kind of roughly sketched before. So let's say that you want to use some resource R. So Alice and Bob share a resource R, which is given to them. And then they want to construct a resource S. And they can, in order to construct S from R, they can run some local protocols, pi A and pi B, in conjunction with exchanging some messages with each other. And what we want is, in the end, when you have a distinguisher interacting with these two, then the distinguishing advantage is as small as you want. In principle, the epsilon should be quite small. So this is the first security condition. And this is for the case when Alice and Bob are both honest. So in this case, we will say that the protocol pi A and pi B are the honest protocols. So this is like the description you write down of the protocol. This is what you would like the parties to do if they're honest. Right. But now, as you may recall, we also had two other cases, which is one case where Alice is dishonest and Bob is honest, and the other where Bob is dishonest and Alice is honest. And we also need some security conditions for that. Right. OK, so this is the first condition. The second is now, let's say that Alice is dishonest. On this side, so the left side is going to be the real protocol, and the right side is all the ideal side. Because Alice is dishonest, we no longer have her honest protocol pi A over there. So Bob doesn't know what protocol she'll implement. So he wants to make a statement for all possible protocols. On the other side, we have, recall that we had for each resource, which was sort of in the mathcal format, mathcal S was really a tuple of 3 resources. And now, since we're looking at the Alice dishonest case, we take the one with the subscript A, which is the functionality that Alice gets when she's dishonest. But you can see that these two will be trivially distinguishable because the interfaces on Alice's side are different. So we need one extra thing, which is that that there should exist a simulator on this side, which can then simulate the behavior of dishonest Alice. So, I mean, if Bob wants to convince himself that this protocol is secure, even if Alice is dishonest, he should at least be able to simulate her dishonest behavior in such a way that, in the end, the distinguishing advantage, there exists a simulator such that the distinguishing advantage between these two sides is as small as possible. And then there's a symmetric condition for Bob. If Bob is dishonest, then Alice should be able to simulate his dishonest behavior with a suitable simulator. Right, so this is basically the same thing in equations. So these are the 3 security conditions that one needs. And if you can ensure that you have these 3, then you would say that the protocol pi, which consists of pi A and pi B, epsilon constructs the resource S from the resource R. Right. Right. So some comments to be made here. So if you can show that a resource S can be constructed from a resource R, then R will be the stronger resource and S would be the weaker resource. Because given R, you can actually get both R and S. Given S, you don't necessarily know if you can get R. So in this case, R would be the stronger resource. And right, and if you want to show some possibility result of this form, that there is a protocol that constructs S from R, then this would be a strong possibility result if pi is a very simple protocol, and the simulators are also very simple, but this is secure against a very powerful class of distinguishers, right? So even a very powerful class of distinguishers cannot really distinguish between the construction and the ideal case. But this is achieved through a simple protocol. On the other hand, an impossibility result would be a strong impossibility result if a simple distinguisher can break a very general class of protocols. So these are the kind of considerations that one would need to take into account. What are the set of allowed protocols and the simulators and the distinguishers, and then this will sort of distinguish how strong your possibility or impossibility result is. Right. So now I'll tell you a bit about the causality part, or the more how these resources, abstract resources, are modeled physically. And for this, we use the causal box framework. This framework itself is very involved, and we won't need, most of those details. So I'll give you a very quick summary of the main idea. So we are going to model each system, which in our case was these resources or protocols or simulators, distinguishers, so on, as a causal box. And what is a causal box? Well, it's essentially just at an abstract level, it's just a CP-TP map with some inputs and outputs, which is, of course, like our standard quantum CP-TP maps. But the difference is that now the messages that you can send in are not just quantum states, right? So, of course, in the usual case, you have the inputs and the output systems of these maps live in some Hilbert space, which denotes some classical quantum message. But in this case, you have, in addition to that, some space-time stamp that labels, okay, this was the space-time location at which this message was sent into this box, and then similarly at the output. And the nice thing is that there is really a separate Hilbert space also for the space-time stamps, and I'll get to an example of this a bit later. And the other thing is that you can also compose these causal boxes. So, for example, you can take compose them sequentially, parallelly, and actually more interestingly, you can actually have some kind of a loop. And this should be interpreted as a feedback loop where, imagine I have a device, I take the output at time t, and then plug that back into the input of the device at a later time. So it's really a physical feedback that which you can do on the wires of these boxes. Right, so in that sense, you should think of a causal box not as a one-time map that's just applied, but more like, imagine like my computer that's sitting around here, and it can take inputs over a whole range of space-time locations and give out outputs, and I can process these and send it back, and so on. Right, and most importantly, these are closed under arbitrary compositions, which is the most important property we need for doing composable cryptography, that under parallel, sequential, and loop compositions, you in the end always get a valid causal box. And the causality condition is essentially that any output of a system can only depend on inputs in its causal past, which you can tell from the space-time stamps. And it can also model sort of messages sent in a superposition of different orders and so on. So it captures quite a few general scenarios. Right. So as I mentioned, we are modeling cryptographic resources as causal boxes. So just to get back to this familiar example of biased coin flipping, earlier we only had these messages. So now we would sort of also add these space-time stamps. And recall that with this biased coin flipping, Bob gets an output first, so at some location P1. And then, depending on this, he can send an input to this box at some later space-time location P2. And then, depending on that, with some probability, Alice can then finally get her output at an even later space-time location PA. And of course, these are all very simple, classical, ideal functionalities we've talked about. So in this case, it's quite easy to see how you would add the space-time stamps. But the protocols that we want to use to possibly construct these or show that it's impossible using a general class of protocols, we would also like to allow for protocols that can, for example, send messages in a superposition of different space-time locations or superposition of different times. So a very simple example is, imagine that Alice's protocol has a state psi at some time t0, and then it wants to send to Bob the same state psi at a superposition of different times, and then you can write it sort of in this manner written here. And this is a valid input to a causal box. And you can also equivalently view this as the second state I've written here, where this omega stands for the vacuum state. So this, you can imagine this as, well, Alice sends the state psi to Bob at time t1 and nothing to Bob at t2. And in the other branch, she sends nothing to him at t1 and sends the state psi at t2. So yeah, so this also allows you to model, like you have basically a whole Fock space where you can model superpositions of any number of messages being sent around. So I won't go into the details of that, but basically all the statements hold against these general class of protocols. All right, so now I can tell you about this quickly about this channel with delay resource that I mentioned before. The motivation for defining this is that a lot of these bit commitment protocols, the relativistic ones, essentially behave more like a channel with delay than a bit commitment that allows you to stay committed for an unlimitedly long time. So these are really timed commitments. So the channel with delay resource we define here is actually quite simple. It has is mainly characterized by these 4 space-time points. So let's look at this space-time diagram. So A and A prime are space-time locations associated with Alice. B and B prime are associated with Bob. So in the case that Alice and Bob are both honest, then it's basically just an identity channel from the location A to the space-time location B. But in the case that, so this would be the description of this resource CD here, because this is the case when Alice and Bob are both honest. In the case that Alice is dishonest, she can actually move up further down, later down this channel, and between sort of A and A prime, she can go and tamper with any messages in this channel, but after A prime, she can't do anything. So in this case, in the case that Alice is dishonest, it's an identity channel from A prime to B. And in the case that Bob is dishonest, Bob can sort of come, intercept the channel at an earlier location, and then it's a channel from A to B prime. But the crucial assumption, the reason it's a resource, is that, this is what I just told you, is that there is this blue region, which is this causal diamond of A prime and B prime, which we call the trusted region. And this is really the region within which neither party, even if they're dishonest, can come and access the contents of this channel. All right, so now to the impossibility results, or possibility and impossibility results. So the first thing is that we show that, of course, given this channel with delay resource, if Alice and Bob share a channel with delay resource, they can actually use this to securely construct, in fact, perfectly construct, which means with epsilon 0, an unbiased coin flipping resource, which is composably secure. And what was known before is that if you are given a bit commitment resource between Alice and Bob, this can be used to construct a half-biased coin flipping resource through what's known as a Blum's protocol. So in that sense, this construction gives you a stronger resource compared to Blum's protocol. And we show that it's secure against quantum and no signaling adversaries as well. Right. Maybe quickly sketch the protocol, because the protocol itself is extremely simple. So as I said, for possibility proofs, you want extremely simple protocols that are secure against large class of distinguishers. So the protocol is basically that now we know that Alice and Bob share this channel with delay resource, which is characterized by these space-time points and regions. Now what Alice needs to do is she uses the channel with delay to send a classical bit A to Bob. And then they choose some point P in the trusted region, such that then Alice has an agent Amy and Bob has an agent Bill who meet at this location. And at this location, Bob gives his choice of an input, B, to Alice's agent. And at some point in all their joint futures, they can go and output this bit C, which is the XOR of the two. So in a way, it's similar in spirit to this coin flipping protocol I showed you in the beginning, which was not composably secure. But having this channel with delay with this guaranteed trusted region actually allows you to perfectly construct coin flipping in a composably secure way. Right. OK, and now for the impossibility result. Right. So, OK. Right. So what we first show is that basically it's impossible to securely construct, composably securely construct a coin flipping resource between Alice and Bob if you don't have any assumptions. So of course, previously what we saw is that if you assume that they share a channel with delay, then you can do it. But if you don't assume anything about what they share, then in that case, it's impossible to construct coin flipping. Even a p-biased coin flipping, so there's really a bound on epsilon that depends on p. So yeah, so for example, if P was half, then you would get that, it's not possible to make epsilon smaller than 1/12, which means that you can always construct a good enough distinguisher that will always distinguish it. So then the security is no good. And then this implies then the impossibility of channel with delay and bit commitment because of these construction results, constructability results. So we had that basically in the previous slide, that given channel with delay, you can do unbiased coin flipping, and also given bit commitment, you can do biased coin flipping. And of course, given unbiased coin flipping, you can always add a bias, so you can trivially get this. So proving the impossibility of biased coin flipping then automatically implies everything else is impossible. So for example, as I mentioned earlier, when you show that a resource R constructs a resource S, R is the stronger resource and S is the weaker resource. So if the weaker one is impossible, then so is the stronger one. So then this immediately tells us that all these are impossible as well, without setup assumptions. And actually, yes, so previously I think people have proposed bit commitment and coin flipping protocols, but in sort of models where you bound the adversary, for example, you bound the amount of memory they have, or the amount of, assume that they only have some kind of noisy storage and so on, and then you're able to show some possibility results. But turns out that even these results in the bounded and noisy storage models are not secure composably because of this result. Yes. Yes. And okay, so the final thing that one could ask is, okay, if I'm given this channel with delay, or let's say Alice and Bob have n copies of a channel with delay, can they construct a new channel with delay that has a larger trusted region? So can they increase the delay of their channel? And turns out this is also not possible without further setup assumptions. So yes, so you can never securely increase the delay of your channel with delay without further setup assumptions. So yes, and this also holds when you have players sending messages in a superposition of order through the different copies of the channel with delay. Indeed. Okay, so, right, so, all right, that was a lot taken, so to wrap up. Right, so, this, okay. Sorry. Right, to summarize, we have this new framework for modeling composable security of these general class of protocols, and the new things we found was that we had this sort of channel with delay resource that we defined, which was quite a simple resource. And then we now know that you can use this to construct coin flipping, in fact, unbiased coin flipping. And if you don't assume any resource, that is, if you only say that assume that there's direct communication between the parties, but I mean, no further assumption about the security of the channels used and so on, then it's impossible to do construct either of these resources. Yes, and also you cannot securely increase the delay, even if you're given n copies of a channel with delay. All right, yes, so I would then conclude by saying that there's a lot of interesting scope for future work, and I feel composability is a key notion of security to keep in mind if one wants to scale up crypto systems. And okay, there are a lot of open questions, but I'll go through them quickly depending on how much time we have. I think we're...
So if you only 10 minutes questions, then you have 5.
Okay, I'll be done in like 2 minutes. It's the last slide. Okay. Right. So, okay, one natural thing given our impossibility results is that what are the minimal assumptions or resources that one needs to assume between Alice and Bob so that they can do composably secure bit commitment and so on. And there's actually some really nice work from Petros Walden's group in Edinburgh, and he has a student, forget his first name, but he has a really nice bachelor's thesis on this. And they actually find some minimal assumptions, and it seems, I'm yet to go through this carefully, but it seems like you can actually, with fairly minimal assumptions, get around the impossibility result. Yes, so there are a lot of open questions there. Then one can ask about further impossibility and possibility results, such as what about relativistic QKD, oblivious transfer, and so on. And Lydia, who's at ETH, was one of the co-authors on this work, along with one of her master's students, recently had a paper on the impossibility of oblivious transfer based on this framework. And then more on the foundational side of things, I would, for example, be very interested in understanding whether this makes sense at all, because so far this causal box picture is all modeled by assuming that there's some absolute space-time stamps with which you label your systems. But what if the space and time information was instead encoded in some quantum reference frames or quantum clocks and so on? Can you still make similar arguments, and what happens to composability there and so on? So I would be very happy to take any suggestions or ideas you have in that direction. And another foundational question is also that composability, apart from being important for cryptography, is also, I think, at least to me, very important to the way I think about physics. You're able to compose physical systems together to build other systems, and it's quite natural to the way we think about physics, right? You have various maps that you can apply on systems, and then you can view this as one big, larger transformation. And of course, with the causal box framework, you also have this for situations where you have these superpositions of orders in space-time and so on. So I would be interested in seeing how sort of process matrices can be embedded into this framework. And we have some work in this direction because, for example, I guess that process matrices are not composable in the same way as, at least in an arbitrary manner. And so we're kind of looking into how you can understand this composability or non-composability once you take a process matrix, embed it in a space-time, and model it through a causal box kind of picture. Yes, and finally, this thing of you can kind of invert the problem and look at physics from the point of view of possibility or impossibility of some fundamental information processing tasks. And this is maybe a bit in spirit also of what Marcus was talking about this morning. One of these rederivations of quantum theory by Jeffrey Webb is really based on, for example, the impossibility of bit commitment and a few other things used as postulates. So yeah, so there's some interesting things also to explore there. And with that, I'll thank you very much for your attention and look forward to questions.
Can you go back slide? Yes, this one. So, something I didn't get was the consequence of this for these other kind of applications. What is now that you've proven this? Does that mean that zero knowledge proof is impossible without adding extra assumptions? You can't. Is that right? Or like?
Yes. Right. So I mean, let's see. So. Yes, so it doesn't immediately imply, for example, for oblivious transfer, right? So of course, we first proved this impossibility of coin flipping, and because it's known that bit commitment and channel with delay can construct that, it immediately implies the impossibility of bit commitment and channel with delay. But in the oblivious transfer case, for example, there's this construction going in one direction or the other way around. So this is where there's this recent work by Lydia and her student which actually show that separately that even oblivious transfer is not possible. So it doesn't immediately follow from our results because sort of the construction goes in the other direction. So this means, I mean, if just looking at this arrow, it means that bit commitment is a stronger resource than zero knowledge proofs. So showing that this is impossible doesn't immediately show that zero knowledge proofs are also impossible.
By proving the stronger resource is impossible.
Doesn't mean the weaker one is.
Yes. Yeah.
So if the weaker one is impossible, then naturally the stronger one is impossible as well. And also another subtlety is that there are some constructions going in the opposite direction, but these are, like, for example, shown to be secure against classical or maybe quantum adversaries and so on. So one needs to show that these constructions also work for this general relativistic quantum settings before then applying our result to say that this doesn't work. So it doesn't immediately follow. So that's a good question. But indeed, like a lot of construction of these kind of zero-knowledge proofs and so on are based on having bit commitment and coin flipping. So given that those can't be done composably, then you would either want to find a different construction, or you want to find like a minimal thing from which you can construct bit commitment and then construct. Yeah. Mm-hmm.
Okay, so in what sense is a resource weaker than another one?
Mm-hmm. Yes, so at least here, if you can show that given a resource R, you can construct a resource S, which is secure in the sense that we talked about before, with that the epsilon is small enough that you can't distinguish it. In this case, that we would say that R is a stronger resource than S, because given R, I can construct S, but given S, that construction itself doesn't tell me that I could also get R. So in this sense, if you can show that you can use R to construct S, then R will be the stronger resource that is. That's right. Yeah.
In this protocol where you have result 1 and you have this trusted region,
Mm-hmm.
and they have like these two extra entities that exchange the bit,
Yes.
they have to be trusted.
Indeed. So in a lot of these relativistic protocols, the assumption is that now Alice can split up into many trusted agents, Bob can split up into many trusted agents, and indeed, so Alice has to trust her agent, and Bob has to. That's needed. That's right.
So is that, because it seemed pretty, when you laid it out like that, it made it seem like channel delay should be kind of somehow trivial.
Mm-hmm.
So is that somehow behind the real reason why you can't do it? Because you're implicitly implying you have some kind of secure channel with these extra parties, and so that's, in the way you lay out, that's like, in a sense, sneaking in like an extra resource. Is that the reason why it fails?
Yes, I mean that, and also the fact that you need this trusted region, right? Like, so you have to be able to ensure that none of the parties can come and change the. So there's a channel between these two space-time locations, but there's like, just for now, think that it's been between two instances in time, but there's actually a time interval in between where neither of the parties can come and intercept the message. So it's, in some sense, really a secure channel between that time interval, and that is hard to ensure just from no assumptions. Of course, if you have some kind of authentication and further protocols or assumptions, then you could do it. Yeah. Oh, thank you. Yeah.
In that case, let's thank Vilasini again.
Thank you. Thank you very much.